Assalamu alaikum. Welcome to lecture 5 of chapter 6. We are still in mechanical properties of metals. It's a rather long chapter because it covers a lot of properties. We will of course review what we did in the last lecture, and then today's lecture we will continue with plastic deformation of polycrystalline metals. We left with Hall-Pech equation. We will complete the discussion. Then we will go to effect of plastic deformation on grains, effect of cold work on strength, and solid solution strengthening. Towards the end, we will be doing effect of heat treatment on strength. So let us see very quickly review what we covered last time. We defined and explained resilience. Then we defined toughness, the area under the whole stress strain curve. Then we talked of toughness and impact testing. What is impact loading? What is toughness? What is impact toughness? What is the Sharpie impact test, the Sharpie V-notch test, and the machine? The procedure for the test with the Sharpie sample and the ISOT sample. We showed you a schematic diagram of the Sharpie impact testing machine. Another diagram where we showed the machine and the height h and h dash and the Sharpie sample and the ISOT sample, and how the energy is calculated during the test. Then we told you about ductile to brittle transition. There are high strength materials which have low impact energy. There are FCC metals which have high impact energy. And there are BCC metals which have high impact energy at room temperature and so on. But if you reduce the temperature to near zero or below, then they go through a transition from ductile to brittle behavior. This covered the initial part of tensile related properties and so on. Then we talked of hardness and hardness testing. How do we define hardness? What is the difference between hardness and strength? How do we do the test? We explained how we do the test by doing indentation. At the bottom of the page, we showed you some natural materials in terms of increasing hardness. We showed you the actual picture of a Rockwell hardness testing machine. And then we discussed the 4 different testing methods and machines: Brinell, Vickers, Knoop, and Rockwell, and the type of indenters and how we calculate the forces and the diameters and so on. We told you that section 6.5 will not be covered, and the next section is plastic deformation of polycrystalline metals, where the first topic was effect of grain boundaries on strength. Then we showed you the strength of a polycrystalline metal and a single crystal metal. We started talking of the Hall-Pech equation, where yield strength can be defined in terms of the average grain diameter. So this was where we stopped last time. Now let us start today's lecture. First, an announcement. I have already sent you by email that midterm will be in week 8, Tuesday 3rd November at 4 p.m. And this is because by the Central Timetabling Committee of the Department of Mechanical Engineering, they have made a combined midterm schedule for the whole department so that there are no clashes. What will be the exact coverage? We will do some more lectures before we reach the midterm, so we will tell you about the coverage later. 1 or 2 students sent me an email that they have another midterm on the same day. That I usually cannot help, and by this time you are already several years into engineering. You know that engineering students are very tough students. Sometimes this does happen that there are 2 midterms on the same day. But there is a lot of preparation time. You prepare earlier. You don't have to prepare on the last 2 days. So you learn to live with it. But for me, I cannot take the pain. There are so many students, 40 students, that if I change the time, then somebody else will have a problem. If I change on a time, somebody else has a problem again. So my advice is that if somebody wants a change, then they can contact all their friends in the class through the email and so on. You have on the email list everybody. And if everybody in the class agrees, then I am ready to change it. As a practice, we told you earlier, I'm doing it. Let us solve some of the problems on quiz 1, right? This gives you extra problems to practice and some thinking. So question 1 was of course MCQs. I will not be able to cover all the MCQs that could be there, but at least some of them. So again, you try to do it with me. Don't read the answers. Materials that produce electric field when exposed to mechanical force or exhibit mechanical stress when subjected to electricity are called piezoelectric materials, shape memory alloys, nanomaterials, electronic materials. So those of you who have prepared well for the quiz and so on know that this property, that if you load the material, if you put a stress on the material, it will emit some electrical voltage or current. Or if you put electrical voltage or current through the material, it will start to bend or show stress. These are called piezoelectric materials. This is a very critical property of certain applications. New processing techniques to improve product life and fatigue properties of metals are isothermal forging IF, powder metallurgy PM, die casting DC, or isothermal forging and powder metallurgy. So again, those of you who went through the lecture notes and the classes, yes, new processing techniques, both of these, isothermal forging and powder metallurgy, both are new techniques which can improve the product life and the fatigue properties of the metals and so on. Fullerene and graphene are types of nanomaterial, electronic material, biomaterial, composite material. So yes, those who guessed it right, they are types of nanomaterials. There are fullerenes and graphenes, and there are carbon nanotubes, if you remember. Most abundant metal in the Earth's crust is, we discussed this for a long time when we were discussing the table, silicon, iron, aluminum, sodium. So we told you that there is a lot of iron, mashallah. It has been enough for several thousand years of engineering, and now there is much more of aluminum because we are doing a lot of aluminum alloys now. But the electronic material, which is the future of the world, is silicon, and it is even much more. So the answer is silicon. Most important material property for high speed, sorry, one E is missing, high speed civil transport. Most important, there are many. So temperature resistance, impact resistance, hardness, all of the above, they are all important. But temperature resistance, because high speed civil transport, if you remember, was traveling at several times the speed of sound. And then the friction with the Earth's atmosphere creates a huge amount of heat, and the whole thing will burn down if temperature resistance is not there. So all other properties are also required, but this is the most important. Metal alloys such as this are used in biomedical applications. Titanium alloys, stainless steel, cobalt alloys, all of these, right? If you remember from there, then in biomedical applications, all of these are important. There are, of course, some other MCQs that we could go through, but again, if you go through my lecture notes properly, and if you go through my sound lectures, these videos, and then at least once you repeat the lecture, then these things are in your mind, and sometimes you do multiple choice by deleting the wrong answer, by not selecting the right one, but by saying this is wrong, this is wrong, this is wrong. Oh yes, this is the right answer. Or if you know the right answer directly, then it is very good. Let us go to question 2 and part 2A. Draw simple force deformation graphs showing elastic behavior of metals and rubbers polymers. For metals, show plastic deformation and elastic recovery after removal of force. So this is just a very simple hand sketch type of thing, that you are drawing a graph. So the vertical axis is force and the horizontal axis is deformation. On that, show one graph for metals and one graph for rubbers and polymers. Elastic behavior only. We are not talking of the whole stress strain graph. Then on either the same graph or another graph, for metals only, elastic recovery after removal of force. Right? So I think you all know it, but so this is the graph on the left. Right? It is force, deformation. For metals, it is a straight line graph. It is a straight line graph. And for polymers and rubbers, it is a nonlinear graph. It is any nonlinear graph. And these arrows above and below and this way are very important, because this means that this is the graph for the elastic behavior. Elastic means when you remove it, it goes back to zero. When you remove the load, it goes back to zero. So, right, so linear elastic for metals and non-linear elastic for polymers. Then there is the graph. This was only elastic behavior. Now, because they are saying after removal of force, what is elastic recovery? So for metals, you should go into the plastic region. So it is the straight line region and some plastic movement, and then you remove the load, right? So you are loading and then you remove the load, you show that. This is plastic deformation, permanent deformation, and this much is the linear, right? This from here till here, you draw a line, and this region is the elastic recovery, right? So this is your graph. Part 2b, a piece of copper originally 12 inches long is pulled in tension, causing a stress of 40 KSI. KSI means kilo PSI. If the deformation is entirely elastic, what will be the resultant elongation? Now, what I forgot at the time of the quiz was, I forgot to give you the E value. E value for this copper is 110 gigapascal or 16,000 KSI. 16,000 KSI. Okay, 16,000 KSI. So if you did it earlier, okay, but otherwise, just for practice, you have done it in the quiz. Pause again and take out your pen and paper and try to solve it again. Take 2, 3, 4 minutes, 5 minutes and solve this once again. It's a very simple one. I did not make the first quiz rather difficult. We will keep on increasing the level later on. So what is the data? You pause it. Well, once you have solved it, you can start listening to me again. So the data is that the original length is 12 inch and it is pulled in tension, and 40 KSI, 40,000 PSI is stress is already there. But we are saying that the deformation is entirely elastic. So what will be the elongation, the delta? What will be the elongation, the delta value? So you have these, and now if it is elastic, then what is the relationship of a stress and a strain in the elastic region? Sigma is equal to E epsilon. Sigma is the stress, E is the elastic modulus, epsilon is the strain. So you can find the strain, and from the strain, then the definition of a strain is delta L upon L naught. So therefore delta L is the elongation. So you can then find it, right? So, right, so a strain is delta L upon L naught. And in the elastic deformation region, sigma is equal to E epsilon. And because epsilon is delta L upon L naught, so I can write sigma is equal to E into delta L upon L naught. So now sigma is equal to this. You know a stress, you know the Young's modulus, you know the original length. So you just rearrange it and you can find that delta L or the elongation is 0.03 inch. If we had given it in the SI units, then the stress would be 276 megapascal, the length would be 305 millimeter, and the 110 gigapascal. So you can find it there. Because of my small error of not giving the value some of you went to the internet or some other places, found the values, so some tried to do it in the SI unit. For now it is okay, but generally this is how it is done.